Okay, I'm going to continue from the discussion of last time where we talked about Snell's Law, where we're going to see what happens when we have light going from one medium to another. So I'm going to say that the light goes from medium N1 to medium N2, or medium 1 to medium 2, where medium 2 is a refractive index N2, and medium 1 is a refractive index of N1. Where N, remember, is the bigger N is, the slower light travels in the medium. Okay, so let's just say that N1 equals 1, which is a vacuum, or else it's close to air. And N2, let's say, is equal to 1.4, which is the refractive index for some types of glass. So what we do is we look at the way the light is hitting, going from one medium to another. So let's just say that the light is this blue line here. So the way I drew it, the light is traveling from, in this direction, designated by the arrow, and the crests of the light wave, if you like, look like that. They're not to scale, where one wavelength is that separation there. Alright? So what we're interested in here is what happens when light hits that medium. Well, it can actually do one of a couple things. One of the things it can do is actually bounce back. It's called reflection when it does that. And the things we're interested in reflection are the angle of incidence, which is the angle at which the light hits the medium. That angle is measured from the angle at which the light is traveling to this dotted line, which is the normal to the medium. So I'll call that theta incident, or theta with an I. And the reflected angle is theta reflected. And one of the simplest laws to remember is that the angle of incidence is equal to the angle of reflection for light. Now for some of the light is going to be transmitted into the medium. So it's going to look like this, where you're going to have an angle here called theta transmitted. And this is where Snell's law comes in, where we have N1 times sine of theta incident equals N2 times the sine of theta transmitted. Alright, so let me give you an example with some numbers. Let's just say that we're shining light at an interface here at an angle, incident angle of 30 degrees. So let's just make theta incident equal 30 degrees. Find transmitted angle theta. Alright, so let's see what happens. New slide. So I have N1, I'll write down Snell's law here. N1 sine theta incident equals N2 sine theta transmitted. Alright, so N1 is 1, N2 is 1.4, theta incident is 30 degrees. So we have that 1 times the sine of 30, or 0.5 as it turns out, is equal to 1.4 times the sine of theta transmitted. So sine of theta transmitted equals 0.5 divided by 1.4. So the transmitted angle is equal to the inverse sine of 0.5 divided by 1.4, which equals about 21 degrees. Okay, so if I were to draw this, I'd have the same thing I drew a minute ago. I'll have my vertical line representing the interface. I'll have the normal here. Then I'll have my light beam, or my light ray, with an incident angle of about 30 degrees. That's this angle. And a transmitted angle about 21 degrees. This is N2 equals 1.4. This is N1 equals 1. And yes, there will be some light that's reflected also. But I'm not calculating how much light goes through versus how much is reflected or anything like that. Just know that at an interface you typically have some light that's reflected and some light that's transmitted. The amount will vary depending upon the angle and the two materials. But the light that is transmitted is going to be transmitted at this angle. And this is what's going to be used for finding other properties of light, or of lenses and things like that. They actually use this phenomenon to bend light to create images. And that's the other part of the lab that you'll see in the next video.